Okay, want to start talking about magnetism. There we go. Okay. Got a moving charge, and I said this the other day, hopefully you kind of reviewed it, sort of have it in your mind, hopefully read it a little bit. But there's your basic definition. Okay, and that's kind of a formula that you go ahead and just make sure you got in your head, but you use it often enough that it becomes obvious. Now, Q is the charge. Is velocity, obviously. And V is a magnetic field. Now, we're not going to say where a magnetic field comes from just yet, but it comes from moving electrons or moving charges. So I will say magnetic field results from moving charges. And acts on moving charges. And as far as we know, that's it. Now, we don't know everything. In other words, I say we, talking about collective humanity, okay? And we just, collective humanity, the being the we, not me, just did some careful measurements over 10 years. And realized that the W boson appears to have a little more mass, about 1% more mass than everybody thought it was. Now, that shouldn't be a big deal, except it undoes the entire theory, the standard model of particle physics. Actually doesn't necessarily undo it, but it means it has to be modified because you just can't have a 1% error in that. And I think that was done at Fermi Labs. Those guys are really good. And people tend to think, yeah, this thing was off by 7 standard deviations, and 5 standard deviations is a limit. If it's over 5 standard deviations, you've got a problem. Now, it's such a big result that nobody's going to really believe it until somebody repeats it, which might take 7 more years. Not an easy experiment to do. You got to have a particle collider. Of course, we got the Large Hadron Collider, which will speed things up a little bit, literally and figuratively. Okay, so my whole, and that just came out in the last week or so. So when I say that that's the whole story of magnetism, nothing's ever the whole story. Okay, it might be the whole story, but how does that fit in all of particle physics? And that's a topic we just really can't get into here. Okay, and you know, I can only go so deep in it, and it's not very deep. So, it's a whole field. Take a lifetime to learn 1/10 of it, even if you're 10 times smarter than me. Nobody's that smart. Well, yeah, a lot of people are. Okay, so, okay, magnetic field results. Okay, there it is. Okay, this is kind of a neat thing. It comes from moving charges and it acts on moving charges. So we'll see what that means. We'll see what the rules are. This is the easy rule. The other one's a little harder. It's a lot like Coulomb's law, but there's a little twist to it. Okay. So what's the result of this? The result of this is if I've got a magnet And of course, you've seen pictures of magnets. If you got a bar magnet, you have one kind of magnetic field. If you've got one of our ceramic magnets, you've got another kind of magnetic field. And it's not hard to visualize that magnetic field. If you have, for example, a cylindrical magnet like this, then the magnetic field pretty much comes out at a perpendicular on each end. It points close to the end. Okay. Now, it's almost like you got two opposite charges. I don't know if you've done everything you're supposed to have done with dipoles. Okay. If you had a positive and negative charge here, the further you move away from them, the more that looks like no charge at all. And the more it acts like no charge at all. And if you write out the expression for the electric field of a dipole, which you hopefully have read and thought about and pondered and tried to analyze a bit, you find that the magnetic field or the electric field of a dipole, two fixed charges, falls off. There's a much higher reciprocal power than the second power, third power, fourth power, okay, at large distances. Depending on your direction, tends to fall off as fourth power, okay? And I think that's right. I should write that out and deconstruct. Just some fairly heavy algebra in it, but nothing that's beyond you. Hopefully it's not beyond me. Okay. It seemed pretty straightforward to me. So this field falls off. So basically, if you move up to here, there's almost no magnetic field. Now over here at a point like this, it's like, well, the magnetic field is kind of pushing away from this end of the bar and pulling you toward this end. It's like pushing you away, but it's also pulling you down. So it's not radial away from this end, it's more like down here. Okay. Now this isn't the scale, this would be much weaker at this point. But, then if you move to a point like maybe here, well, it's being pushed away from this, but see, pulled down to this one a whole lot more than this one was. You know, if this one was straight away, it'd be here, it's just pulled down a little bit. This one would be straight away, but pulled down quite a bit. So it might be like this. And by the time you get here, it's pushed away here, it's pulled in here. The vertical components cancel out, much like in the case of some of the electric fields that you hopefully have worked on and worked with. Okay. And then kind of, get down here and or maybe at a point like this. Now it's pulled into this, but it's pushed away from this, so it's maybe like so. And what you end up with is a magnetic field that sort of follows lines like this, comes vertically out of here and loops around. And does the same thing on the other side. And if you're in closer, yeah, it does the same thing. The magnetic field's bigger in here as you're closer to the poles. And so forth. So if you did the field a little more accurately, you might have a field that looks like this. Around here. And then a weaker field along these lines and a much weaker field along these lines. So we can measure that. And we probably will in lab Friday. Okay. So that's kind of the way your magnetic field goes. You see better pictures in your book. And we got a question. Okay, I said something about lab on Friday, but turns out it's Good Friday. We're off on Good Friday, so week from Friday. We'll probably mess with Magnus maybe a little later today or Wednesday. When we see. Okay, well, we're not going to be able to do electron beams because it involves high voltage. Okay. Deflecting electron beams with a magnet. But it's not too hard to understand what happens. Okay. Back to this. If you have an electron, well, let's just work it out. So you got an electron moving north. Out. How much about knew what exponent I was going to use. I don't want to match my exponent with my number. So I wanted kind of a big number. But I'll go 8 times 10 to the 6 meters per second. Okay. So what's the value of QV? Now QV is a vector, so you have to give me a magnitude and a direction. Not what did it make a point we want to not forget? Explain from the camera. Well, it's clear that it's nothing to it to get the magnitude of QV. Now, when I wrote down 0.6 times 10 to the negative 19th coulombs and posed the problem, question of what's the direction of this QV, didn't get a real good answer. But of course, you got to realize when I wrote down the charge as this, I just write down the magnitude of the charge, but I didn't say that. So you blame it on me, but it's negative 1.6 times 10 to the negative 19th coulombs. Okay. So what's its direction? Well, V is north. QV is a negative multiple of a vector that's north, which is south. Okay, and in this lab, north is right about there. So south is right about there. Okay, and can't really see that in the screen, but wherever north is, south is in the opposite direction. Okay, so it's south. Now, let's say you've got a magnetic field in here. Okay, I'm going to say B equals O2 Tesla, not Tesla. O2 Tesla. And after Nick Tesla. We call him Nick. Okay. He died when I was just, in early middle age. You look him up. Very interesting, eccentric guy. Did some profound stuff, but didn't work out for him that well. Okay, so anyhow, you got this magnetic field, right? Now you've got to have a direction because you got to do a cross product, right? So I'm going to have that direction be either up or down. So just show me with a finger or something. Do you want it up or down? Whichever you wish. Up, down. Okay, you do it up, you do it down. Or maybe I ought to switch and you can stick with the one you chose. Okay, So let's say up or down, you choose. Okay. What's that? Just to move things along a little bit, magnitude of F is QVB sine theta. The magnitude of QVB sine theta. The direction is by the right-hand rule. So it's real easy to figure out the direction here, since one of these things is north, which is in a horizontal plane, and the other is vertical. You just got to get your right hand in the right position, and you can tell me what the direction of the force is. And this is a definition of the cross product. And there's a determinant form of it. That'd be overkill right now. We don't need it. We just need the definition of cross product. If you don't remember that, well, you just got it reviewed. Okay? Okay. So what's theta? It's the angle between QV, which is south, and either up or down, right? Now, south is perpendicular to up and it's perpendicular to down, so the theta is 90 degrees in this case. That's magnitude of QVB. The magnitude of QV is capital T for Tesla. Yeah, just this, which we calculated, and this, which I gave you, which is then 2.88 times 10 to the negative 14th kilometers per second times Tesla. Well, okay. And that should equal newtons if Tesla is an SI unit, which I declare that it is. And everybody else agrees with me on that. Good for them. Okay. This convention. I mean, it's the definition, it's SI unit Tesla. Okay, so tell me what the unit Tesla, what's Tesla in fundamental units? Got it? Okay, in standard units, this is actually not going to be standard units, okay, because Coulomb isn't a standard unit. Used to be, okay? And you still see it on a lot of tables, so it's worth seeing it. Okay, well, if Tesla times Coulomb meter per second is newtons, Tesla better be Newton seconds over Coulomb meters. Trivia, okay? Yeah, just multiply by the reciprocal. And if I did something really stupid, don't just sit there looking with a confused expression on your face. You know, point to your head and something like this, you know. Give me a gesture that I did something boneheaded, okay? But anyhow, there it is, okay? And that's a kilogram meter over Coulomb meter second, which is a kilogram over a Coulomb second. And I'm not going to write that out because I don't have room. Okay. Now, a kilogram over Coulomb times second. You agree? Now, the reason that isn't a standard unit is coulombs aren't standard units anymore, amps are. So knowing that amps are their fundamental unit, how would you modify this? Okay, well, we spent just a little more time than we really probably should have dealing with the fact that Coulomb's not a fundamental unit anymore. And you were able to tell me it's an amp, but there's a little hesitation. Tell me what an amp was. You know, you knew it was measure current, you knew that was I, but what is an amp? So I had to maybe drag it out of you a little bit that an amp is a Coulomb per second, which should be the most obvious starting point for understanding current. So you want to kind of just reflect on that. You know, why was that not your starting point? Especially since you really like to reason things out by units. Okay. Still, I think we understand it at this point. And you can say, okay, well, what's an amp? It's a Coulomb per second. So what's a Coulomb? It's an amp second, right? And you got amp seconds times meters divided by seconds. It gives you amps meters. Right there it is. Now, even more obviously, you should recognize quickly that Coulomb per second is an amp, and you don't have to do the algebra of expressing a Coulomb as an amp second, which is a little non-intuitive until you really get used to it. Okay. So now this implies that Tesla is a Newton per amp meter. It's written a little small. I'm not sure you can see it from back there, but it should be obvious. Okay. So there you have it. Don't ever forget it. And always, I mean, you can forget it. But using this and knowing that B is in Tesla, you can always figure out what the unit Tesla means. Either a Newton per amp meter or kilogram per Coulomb second. It's the same thing. If I did this right. So make sure I did. Okay. Now the question is, what's the direction of this force? In the case where one of you where the magnetic field is up, the other where the magnetic field is down. So think about it and then point in the direction you think the force is. Got some hesitation on this from some of the class. It should be totally obvious. QV is this way. Now, if you thought QV was this way and used the right hand properly, well, you're okay with the right hand rule, but you got to remember QV is there. And just because we found the magnitude doesn't mean that we're finding the magnitude. We're finding the vector, right? Okay. So if you think the magnetic field is upward, then you're going to cross this with this. So you put your fingers this way and turn your hand in such a way that you turn your hand toward this. Then there it is. Okay. So if you think the magnetic field is up, force is to the west. Okay. If you think the magnetic field is down, then you're going to have your hand like this, and your magnetic field or your force is going to be to the east. Okay, so If B is upward, your force is to the west. That's where QB is to the south. And the first response I got, assumed B is to the north. Well, that's a direction the electrons are moving in, but if it was a proton beam or proton moving north, then yeah, would have been this. Okay. I don't want to say what QB is. I've already said it. That hasn't changed, but if B's downward, the force is to the east. Okay. Okay, now you've got a particle moving this way with a force perpendicular to it. So that's going to change its velocity in a short time. Its velocity will be this way. Okay. Now what's the direction of the force going to be? Well, QV is going to be that way, and it's turned a little bit this way, but QV cross B is then going to be a little bit to the north or west, right? Alternatively, if B is downward, it's going to be a little bit to the south of east. Okay. Now, yeah, I'm dealing with two things, and I got things confused a little bit just in my head, so let's come to gesture, right? But, okay, so you're now moving this way, and your force is a little bit to the north of west. Well, west is here, northwest is here. That force is still perpendicular to your motion, right? And then it's going to change a little bit more, and the force is still going to be perpendicular to your motion. Force is not changing. What kind of motion is that going to give you? Okay, now, if your force is to the west, I kind of gestured wrong. It was just kind of, I just gestured wrong. Okay, so you're going this way. If the force is to the west, it's going to deflect the electron in this direction, right? It's confusing. That, yeah, that's what we get for using two different orientations. Easy to confuse me. Okay, so we're here and we're deflected a little bit here. And now the force is a little bit to the southwest. Okay. And then we deflect a little more, the force is a little more to the southwest. It's always perpendicular to the motion, and it's always in the horizontal plane. If this thing starts out in a horizontal plane with a vertical magnetic field, whether up or down, the cross product is going to be in the horizontal plane. So the thing's not going to move out of the horizontal plane. It's not going to go up like this. It's just going to go in the horizontal plane. And whether the field's up or down, it'll be deflected this way or this way, but it's always going to be deflected in such a way that the force is always perpendicular to it. Now, if you have a force that's always perpendicular, the magnitude of the force isn't changing, because a force perpendicular to your motion isn't going to change your velocity. It's only going to change your direction. Okay? So without writing all that out, I'm just going to say that that's the condition for circular motion. You have a centripetal force. Okay? The result is circular motion. I gestured to show that. Okay, and talked about all the conditions. Okay, the force is always in the same plane as the motion. So you're not going to change the plane of the motion. Okay, the force is always perpendicular to the magnetic field, so it's always constant. Because a force perpendicular to your direction of motion, that force perpendicular to direction of motion doesn't change your speed. And only the speed influences the force. Okay? Your centrifugal force is your magnitude, magnetic force, okay? Which is mv squared over r perpendicular. I'm not going to write out the vector form of that, although that's not difficult. It's a little, for purposes of time. I'm just going to say it's mv squared over r perpendicular to your velocity. It's equal to the magnitude of QVB. This is already positive. I don't need absolute value signs around it. All these quantities are positive. As long as this thing isn't moving so fast, you have relativistic effects. This is easy to compute. Okay. That's easy to charge to accelerate electrons into relativistic range, in which case you've got to take relativity into account, which isn't too awfully difficult. But just throw that caution in there. Okay, so we get the radius of curvature of an electron in a magnetic field. Meaning, if we have now an electron beam created by a certain potential difference, if we know the voltage between here and here and start an electron out here, low velocity, we can easily calculate its final velocity because we get the change in its kinetic energy. Okay, the potential difference gives us the change in its potential energy, which we then use with the work energy theorem to easily calculate its kinetic energy, therefore its velocity. So it's an easy calculation, standard calculation. You got to be sure you know how to do this, okay? Got to be sure you know how to work this out. Your book gives you more explanation, probably does this example. But it's important stuff. And of course, with a proton beam, it's the same thing, just that your mass is almost 2,000 times as great. And you should understand that about electrons and protons, okay? Proton is almost 2,000 times more massive. One application of this that allowed us to actually, allowed physics, Millikan, to actually Millikan measured the mass of an electron. Thomson did the ratio of mass to charge to mass ratio. Interesting setup. Okay, electron beam moving north is going to be deflected either right or left, depending on whether the magnetic field's up or down. Okay. What direction then would the electric field have to have in order to counter that fact, in order to counter that effect. That won't be, it's going to have to, well, we'll see in a minute. We'll talk about this. Okay, now the setup, essentially what we'll have, we'll get an electric field from two plates of a capacitor. Okay? And the electron beam is going to be aimed right between those two plates. But there's going to be a magnetic field, either up or down, that deflects the electron beam as it goes through these points. It's got a radius of curvature of, say, 5 meters. Well, there's not going to be that much deflection in here, but there's going to be some. It's going to change direction a little bit between these plates, okay, from the magnetic field. Now we want an electric field that counters that. So let's assume that the magnetic field is down so that the magnetic force is in this direction. Which plate should be positive and which plate should be negative in order for the electric field to exert an equal and opposite force in this direction? Okay, if the electric field is in, let's say, that direction, which is not what we want, okay? It's in that direction, okay? Then what is the direction of the force on an electron? Yeah. Direction of a force on an electron, you have an electric field in this direction, it's going to deflect an electron in that direction because the electron's negatively charged. Just do the vectors. If you want to use a formula, you shouldn't be using a formula to answer that question, but you can answer it by a formula, which helps you understand the formula and also the concept. You know, it's QE. Okay, if Q is negative, QE is in the direction opposite E. Fundamental fact of vectors. Okay, make sure you've got that. Okay, so which plate should be positive and which plate should be negative if our magnetic field is down? If our magnetic field is down, then the force is to the east. So we want a force to the west. So our electric field had better be to the east, right? Better be in the same direction as the magnetic field. Not the magnetic field, but as the force on the electron, in order to give it a force in the opposite direction. Okay. So there we pretty much have it. So which plate should be positive, which plate should be negative? Okay, got a plate here and a plate here. We want an electric field in that direction. Should this plate be positive or should that plate be positive? Okay, that plate should be positive because your field goes away from positive because your field is in the direction that a positive test charge would be accelerated. Okay. And if you have a positive here and a negative here, then the positive charge is repelled from the positive and attracted to the negative. Okay, now you should digest all that. Otherwise, you don't have a conceptual basis to go with the mathematics. Then you're going to end up not being able to easily think through challenging problems and set up situations in lab. Okay, if your beam is being deflected in this direction, if you want to counter this force by a force in this direction, you set up your plates so that the electric field is in this direction so that it'll accelerate a negative charge this way. Okay, so your electric and magnetic fields have to be crossed. Okay, your magnetic field is down, your electric field is this direction, so they're at right angles. They got to be crossed in the right direction, so your electric field has to, you got to set up your terminals. Take your source, make sure your leads are in the right place. Okay, so you get an electric field between the plates. It doesn't take all that much electric field to deflect the magnetic field because the charge in electrons in the order of 10 to the negative 19th SI units, and the mass of electrons on the order of 10 to the negative 31st SI units. Okay, so you think about that. You need a pretty strong magnetic field, but then it doesn't take a huge electric field. Okay, so I'm just going to say that across. Cross electromagnetic field can result in undeflected beam. Velocity or speed turns out to be just E over B, which is easy to derive. Okay. I might have said that wrong. You might need a pretty big electric field because this has to be a lot bigger than this to give you like 10 to the 6 meters per second. Okay. So your magnetic field probably won't be as strong as 0.02 Tesla. But Earth's magnetic field's in the order of 10 to the negative fifth. Some or some small number times 10 to the negative fourth Tesla. And it kind of fluctuates. It's constant everywhere. Okay, but you need a magnetic field that's not big enough to kind of overwhelm the Earth's magnetic field. Okay, so if you have 10 to the negative second Tesla, you'd want an electric field on the order of 10 to the fourth newtons per coulomb. So on a capacitor, how much charge do you need on the capacitor to get 10 to the fourth newtons per coulomb? Okay. And how much voltage do you need in that capacitor? And I was talking like you need a whole lot of voltage in the coil, which is kind of true, but you do, I think, need a good bit of voltage in the electric field. I haven't done this experiment in 50 years. And it was in a lab that was all set up, and it was almost a cookbook lab. But it was easy to understand what was going on. So I don't have a good feel for those numbers. Should have worked that out. But that's easy to calculate. Okay. And it's easy to see why it's E over B. Because your force from the electric field is QE. There's your force, right? Well, your Q is the same, both numerator and denominator. That goes away. You got a B here. Well, you set that equal to force. Okay. And you end up with, you got something on the other side. You multiply both sides by V and you get this. And everything else goes away. Okay. So I'm not going to write it out because something else I want to talk about. It's important. Okay, so that's really cool. I really thought that was when I first saw that. That allowed physicists who were able to measure the charge on electrons by the Millikan experiment, which I think you might have read about. You'd have little oil droplets, and you create an electric field that holds some of them stationary. And then you measure the size of the oil droplets with a kind of a microscope with a scale on it. So you get their mass, so you know how much charge there was on that droplet. It's the charge necessary for the electric field, which you know, to exert a force equal to the weight of that droplet. And you do that for a bunch of droplets, and you see that all the forces are multiples of the same thing. And that same thing is the charge on a single electron. Okay. And to get charge in the electron, you just spray them out of an atomizer, and that creates a little static. So you get a few to several electrons on the really small drops. And it's a really cool experiment. A friend of mine back 35 years ago, he was teaching physics up at Emory. And we worked on their Millikan apparatus. And we kept trying. We could not get it to work. We could not get it to behave. We get the oil droplets, but I forget exactly what it was, because we never did resolve why it didn't work. Everything should have worked, but it didn't. As a result, we don't do that experiment here either, but it's a neat experiment. And you probably do that in a more advanced class. Okay, so you get the charge, you get the mass, and that's, you get the charge and you get the charge to mass ratio from this whole thing. You know, your cross-magnetic electromagnetic field. So then you know both the charge and the mass. That's how the charge of an electron and the mass of an electron were determined. Good stuff, good stuff. Okay, well, another thing, if you've got a current in a wire, and we're running short on time, but for reasons that are pretty apparent, if you multiply the current in a wire by the length of the segment or the length of the wire, it's equivalent to multiplying a single charge by velocity. Okay, because you got all the charge in that length moving at whatever the drift velocity is. Well, I can't utter the words quickly enough in the short time we have in a way that you're going to understand anything that I said. And the stupid camera is just focused. You're seeing all of me, which has got to be a terrible thing. But aside from that, you're not seeing the board, and that's what's really important. Okay. There, I think I zoomed in once. No, that's good. Thought I zoomed in once too much. Okay, so trying to write an F, write an I. So. I'm taking I as a vector times the length, because the wire has a direction. Okay, we're talking about a straight wire. And that's equivalent to the sum of all the q's times the drift velocity. Okay. Add up all the charges that are drifting and multiply it by the drift velocity, all the charges in that length by the drift velocity, and you get the same thing as if you just take the current times the length. And that's not too hard to see. Okay. That means that if I have a wire, a loop of wire, and so I got a current running in this direction. If I've got a magnetic field, let's say going into the board, okay? magnetic field into the board. Then my IL is here. And my ILB would be in this direction, right? Then ILB would be here. The force would be here. Okay. Now, ILB here would be this way. ILB here would be this way. ILB here would be this way. So you get similar forces. Here are your ILs in this direction. Here are your ILs in this direction. Here are your ILs in this direction. Your forces are always inward. So they tend to implode this wire. But the forces are not that great. So the wire is probably going to withstand it unless it's really wimpy wire, really thin wire. Okay. Now, if let's say we're looking on the end of this thing, okay? So we're just looking at this end. So we turn this wire, we rotate this thing like so. And that's not the direction I want for IL. Well, okay, we can do that. Okay, so IL is in this direction. Again, your force is in this direction. But now this thing is oriented like so. And it's rotating about this axis. Okay. Then over here, your IL is in this direction and your force is in this direction. So the force in this thing is in this direction. The force in this thing is in this direction. The forces on these aren't going to matter because these things are strong enough. Whatever the forces do, turns out they end up not doing anything. The force on this part of the wire and the force on this part of this wire have equal and opposite effects in rotation. They have no net effect on rotation. You need to work that out. We don't have time to go over the whole thing. This creates a torque. Well, that's why electric motors work. Okay, because you've got a magnetic field and you've got a current. When this thing, okay, let's say you've got a loop that's oriented like this and a magnetic field that's down. Current in this side of the loop's going this way, magnetic field's down, current across your magnetic field is in this direction. Here, current's going this way because it's going around the loop. So now the current times the magnetic fields like this, that's going to rotate this thing. Now, when it gets down into this orientation, there's no net force. Okay. In other words, this one's getting a force in this direction. This side's getting a force in this direction. It doesn't tend to rotate. But anytime it's not in this plane, it has force that tends to rotate it. Okay. If you have an alternating current, well, you can read about it. Okay. The fundamental idea is that you can rotate a loop. And we've actually done it. This actually works if you use what's called a commutator. Okay, this little thing here. This was built by a guy who went on to MIT. He's now an engineer, troubleshooting everything for a very dynamic company in Boston. Okay, see his dad often at the farmer's market. Dad's a PhD biochemist. really smart guy. So he sat around trying to get that to work. So it's stuck around the lab. And we'll talk about how that works when we have time to mess with it. Okay. Okay, very good. You want to read through the entire chapter. There's stuff that we didn't yet talk about, but those are the two biggest things about magnetic fields. Then we'll look at some of the details on the rest of it next time. And then next week, we talk about the sources of magnetic field. You know, how do you, why does that thing generate the magnetic field it does? Why do those coils represent them? Create the magnetic field that I say they do? Why do you have that right-hand rule around the core?